So in this video, we're going to look at a really important concept for the rest of your engineering curriculum. It's not overly important for this course, but it's this idea of what it actually means to be a step function. So a step function is, of course, not a function at all because it is not defined at t equals 0. It has an ambiguous definition. So as you move on through the remainder of your coursework, you'll see this is actually called like a generalized function or maybe even a distribution. That's particularly the heavy side distribution. But for now, just view it as the step function and view it as basically what it represents is before the step function turns on, the response is 0, and after it turns on, the response is 1. And the key point is it stays 1. You're going to see when you study linear systems that this is a more specific example of the general type of input that characterizes the response of the system, which is its actual an impulse response. So an impulse function, basically all the energy is concentrated at one point in time. In the unit step function, it goes from 0 to 1. Like any function, or in this case, any generalized function or distribution, you can actually shift it in order to make it turn on at some delayed point in time. Namely, if we subtract t0 from the argument, all that's going to do is delay the onset of the step function to t0. So to go from 0 up to 1 at time t0. So if you ask yourself, like, could you use this to monitor pulses? Well, yeah, you can. If you were trying to monitor this pulse, you could just have one step function that turned on at t0. So like u of t minus t0. You could have another step function that turned on at t1, u of t minus t1. And what would happen if you subtracted those two? Well, this one's going to turn on at t0. It'll be on forever. Then you subtract away the one that turns on at t1, and you end up getting a pulse. So that's how you can make pulses using the differences of actual step functions. And of course, you can take these pulses and you can multiply them by continuous functions like sinusoids, and you can actually get pulsed sinusoidal functions. So all of this will be very valuable to you later on. What we're going to see is in the actual next video, the response that we're discussing is the step response of a circuit. But basically all that's happening is you have a DC source that wasn't connected, and then all of a sudden you're going to turn it on. So particularly when you get into the Laplace transform content, oftentimes it will be valuable to actually model this as a step function because you'll work it in the Laplace domain. But for our instantaneous time domain analysis, it's not really going to add any additional value. So I'm not going to use it in my actual analysis. But since it's such an important topic, I wanted to make sure that you could say you've at least seen it and been introduced to it before.